would have fallen in on a retrograde orbit on an inclination between 30 and 60 degrees. And actually, you only get sharp features if the object was a disk galaxy. But this, to me, was not enough. I mean, it sounds, sounds suspicious. You get excited. So then we went one step further and looked at the chemistry of the stars. And so we looked at the Apogee Survey. And what you're seeing here is alpha over iron versus iron for an apogee sample within 5 kiloparsecs. So alpha is produced by supernovae type 2 massive stars, iron by type 2 and type 1s. So what you expect in a given system is that alpha to iron, you have the first supernovae, the massive stars kicking in, so alpha to iron is flat, and then it drops with time as new stars, as say the lower mass stars are evolving and exploding as supernovae type 1a. So you see here the thin disk, the thick disk, and the stars that were part of the blob are actually this sequence. So they define a separate sequence in chemical space. So that's exciting. But what's more exciting is that because they follow this sequence, which has a lower alpha to iron at the iron of the thick disk, that tells you that these stars did not form in the Milky Way itself, because alpha to iron has always to decrease in time, and so you could have never formed these stars in the same system as these stars and trick stars. So that immediately tells you, okay, these are really accreted stars. What's also interesting is that you can tell, you can look at the ages of these stars and these stars, because at that point you can say, okay, there was a merger. We can actually tell how significant it was from fitting the chemical sequence, and that gives you a mass of, in stars, of 6 times 10 to the 8 solar masses. But then the question is, when this fell in, was there a disk or not at the time? How did the Milky Way look like at the time? Was it really a significant merger? And indeed, if you look at the ages of these stars and you compare them to those, you can then go back to this sequence, and now it all makes sense, because this would be your thick disk still, and this is really this sequence, this other object. And it turns out that the stars here, so the ones that are the most metal-rich stars in the blob, actually are younger than the stars that were there in the thick disk. So there was a disk at the time. And so if you have a merger with an object that is this massive, then actually you can tell that it would correspond to a mass ratio of 1 to 4 roughly, that must have led to the formation of the thick disk in a general sense. So both to a lot of heating, but also probably triggering a lot of star formation in the disk itself.
How long ago did this happen?
Yeah, so you can tell from the ages that it's redshift 1.8, about 10 gigayears ago. So we produced this movie that actually we had it in-house of what happens when you have such a merger, and you can see that whatever disk was there is very, very significantly disturbed, and that many of the stars that are in this disk do end up having, halo-like orbits, which is what we're seeing now.
This is what?
The halo.
10 to the 8, 10 to the 9 years old.
This is, okay, so this movie runs for about 2.5 gigayears, but this supposedly happened 10 gigayears ago, roughly. Okay, so at that point we thought, okay, we have a major merger that happened to the Milky Way with a respectable galaxy, so we should give it a name, and then we gave it the name Gaia Enceladus. And it turns out to be very interesting because Enceladus is a giant in Greek mythology, actually. And so we're looking for giant satellites, right? So this is a respectable object. But it turns out that Enceladus was the son of Gaia and the sky in Greek mythology, which made it even more interesting. And it's currently buried under mountain and responsible for seismic activity. And that's actually, it's buried in the Milky Way, in the Gaia data, and it has shaken it quite significantly.
What do you do about the misunderstanding with the satellite of Saturn.
Yeah, so that's why the Gaia is here. That's why it's Gaia Enceladus. Okay, so it was a respectable galaxy, probably similar to the LMC in its early days. So if you look at the chemical composition of the stars, this would be Enceladus, and this is the LMC. So you can see it's kind of the low metallicity tail of the LMC matches that of Enceladus. So most of the analysis that we did was based on a small sample of nearby stars. So then we looked for more members by looking into energy and angular momentum space, and we selected basically this region of the diagram to find where the stars were. This is just a density map. So you can see here, this would be the disk mostly, and this over density corresponds to Enceladus. And so we're looking at where the stars are on the sky. We found about 30,000 stars associated to this object in the R2. This is the spatial distribution, which is color-coded by how far the stars are. So in purple, you see stars that are nearby, and they are all over this place. And this, in yellow, you're seeing stars at about 10 kiloparsecs from us.
So these stations typically don't have velocities.
These stars, they, in fact, these do have.
They do.
This is still the 70s, the 60 sample.
Oh.
Because we needed to select on the basis of angular momentum, and so that's where we had to use the velocity. One of the things we also did is we identified about 13 global clusters associated to Enceladus, and they actually turned out to follow a tight H metallicity relation. I'll show that at the end. And if you look at the velocities of the stars on the sky, and this is separated by different proper motion directions, but if you just focus on one of the panel, what you see is the color indicates the line of sight velocity. You see the nearby stars really are moving together through space, and that is reminiscent of the streams that we were seeing in the simulations. And one can quantify that. There's very clearly an excess of stars with very similar velocities, so the velocity vectors are significantly aligned compared to what you would expect from a random distribution. So the streams are clearly there. So that was the first thing, or one of the first things that got us very, very excited, because this is really, a big merger that happened to the Milky Way 10 billion years ago. There are some other structures, as I showed at the beginning. We see these structures. These two objects are the ones, these two streams are the objects that Anna was referring to in the introduction. These are streams that I discovered in my thesis using Hipparcos data at the time. I had at the time, this is a sample of 200 stars, and these were, I think it's 13 stars that fall into this region. Now with DR2 within a kiloparsec, we find 40 members, but one of the things that still remains is we find many more stars on this side than on this side, so moving with velocities, say going down through the disk compared to those going up through the disk. And then what we did is we combined this data set with, because we have so much proper motion information in Gaia, but we're missing the line of sight velocities in DR2, we combined this with data from Apogee, Rave, and Lamos to get line of sight velocities for those stars. And we looked again into, say, energy and angular momentum space, or angular momentum, say, in the direction perpendicular to rotation, and you can see this over density of objects really clustering there that corresponds to those two streams. And we could also identify some stars in the direction of the anti-center just on the basis of the proper motion. So at the end of the day, we have a sample of something like 600 members, which is very respectable compared to the 13 we had initially. So we can look at what is the spatial distribution of these stars, and one of the things you see if you look at the green points is that it seems to be elongated a bit in this direction compared to in this direction. So this is the vertical direction, so it's like the stars are going through the solar vicinity mostly. And this is really not a selection effect due to the sample, because if you look at what is the distribution of stars, it's a function of distance from the position of the sun for the background for a random sample. Then what you get is this distribution, whether the stars that are members of the streams follow this distribution. So the stream is really very concentrated in radius, and it's mostly elongated in the Z direction.
Before you leave, will you eventually be showing us a diagram that shows this information in right ascension and declination?
They are all over the sky.
I'm sorry.
They are all over the sky. These stars are all over the sky. Because we're in the middle, we're fully surrounded by this material. So effectively, these stars are going through the solar vicinity. So that's why it's not so useful to see it projected on the sky. It's very kind of a very isotropic distribution. If you can take the velocities of the stars and integrate the orbits, and so for what you're seeing here is the orbits integrated forward and backward in time. We're here at the position of the sun. And what you see in blue is the stars that are crossing the disk with negative velocities from up to down, so they're going like this. In black, you see stars that are going up. And what you see is it's not a single flow, but you're actually seeing, and not even two flows. I mean, you see some moving in this direction, but you also see some black moving